Hello, in this video I'm going to solve the following problem for you on the topic of elementary properties of groups. Let star be the binary operation defined on R by A star B equals to A plus B minus AB. Due to the presence of a single real number, the system R and a star does not form an abelian group. Which real number is that? Motivate your answer. That is a good idea to pause the video at this point and give it a try yourself. If you understand the problem in the correct way, the answer will be 1. Okay, now let us solve the problem. To present a clean and a straightforward solution, I will actually start by proving that the real number 1 with respect to this binary operation has no inverse. How I could get suspicious that the real number 1 is the culprit in this problem, you will see in the continuation of the solution. But of course, because I already know that 1 is to be blamed, so I start with a clean and straightforward way of presenting my solution, as usually mathematicians write when they do some work in a scratch paper and then turn it upside down and present. Okay? So be patient, let us see, and probably you will immediately understand when the problem continues, you will see that why you could get suspicious that 1 is the problematic number. Okay, so my goal is to show that the real number 1 has no inverse. In order to talk about the inverse, I have to know the identity element. So I simply claim that the identity element of the group, which I denoted by E here, is 0. In order to support my claim, I pick any real number, so I would say that A is an arbitrary real number. I have to convince myself when I do the operation on A and 0, it becomes equal to 0 star A, and it gives me A back. But this is very easy, yes? Because, for example, if I want to write A star 0, I use the definition of the binary operation. So A star B is equal to the first element plus the second element minus the product of these two elements. Yes? So I will do the same. The first element plus the second element minus the product of these two elements. But this is nothing except A itself. Yes? Because that's 0, that's just A. And of course, it is also very simple to show that the other way around is also true. The first element plus the second element minus the first element times the second element, that also becomes simply A. So yes, E equal to 0 is indeed the identity element of this binary operation. Now, my claim is that number 1 has no inverse with respect to this binary operation. So let us assume, in contrary, that, for example, element A is the inverse of 1. Then it means that A star 1 should be equal to 1 star A, should be the identity element, which we discovered to be 0 here. Okay? So let me repeat. My claim is that 1 has no inverse. In contrary, I assume that A is the inverse. Then it means that A star 1 should be equal to 1 star A, should be equal to the identity element of the group, which discovered to be 0. Yes? So, but now let us see what happens. A star 1 equals to 0. But A star 1, according to the definition, the first number plus the second number minus the product of the first and second numbers equals to 0. But then this is minus A and A are canceled, and I get 1 equals to 0, and that's a contradiction. So it means that 1 has no inverse. If 1 has no inverse, of course, this ordered pair of a set and a binary operation on it uh, does not form any group, yes? Because at least one element there does not have no inverse. Okay, so now to support the claim that is the only culprit, it means that if I take it off from my set, then the new ordered pair, so let me write it here, I take element 1 from it, and my claim is that now the new system is indeed an abelian group. Okay, so how should I do that? I have to start checking out all the axioms of a group structure. Okay, the first one is closeness. In the previous case, I was not worried about closeness, yes? Because if you give me A and B from real numbers, if A and B are real numbers, this combination is definitely a real number. So it means that A star B is again within my set. So the set of real numbers is of course closed under this binary operation trivially. But here we have a little bit of problem, yes? Because now I have to choose A and B not from the set R, I have to choose them from the set R minus 1. Okay, so I want to make sure that this is indeed a well-defined binary operation even on this new set. So how should I convince myself about that? So I would say that if you give me two elements from this set, is it guaranteed that A star B is still in that set? Okay? This is the question that I have to convince myself to be true. Then I can go to the next steps. But let me write it a little bit differently. A and B belong to this set means that none of them is equal to 1. They are real numbers, but not equal to 1. So in other words, I am asking this question. If A and B are real numbers, but they are not equal to 1, is it possible to conclude that A star B is a real number which is not equal to 1? In other words, can I guarantee this? Okay, in order, I can prove this directly, but I prefer to use the contrapositive equivalent of this implication. So you know that P implies Q is equivalent to contrapositive statement of not Q implies not P. So if instead of proving this is true, I can prove that this one is true. Okay, so giving the role of P to this and giving the role of Q to this, let me write the contrapositive. So this goes here with the negation. A star B is not equal to 1. Its negation becomes A star B is equal to 1. Then this is the negation of this statement. This statement means A is not equal to B, A is not equal to A is not equal to 1, and B is not equal to 1. Okay? What is the negation of this? We have De Morgan's law, yes? The negation of P and Q is equivalent to negation of P or negation of Q. Okay? So the negation of this statement becomes the negation of A is not equal to 1 or negation of B is not equal to 1. Negation of A is not equal to 1 means A is equal to 1, or this means B is equal to 1. Okay? So the negation of this that should come here becomes A is equal to 1 or B is equal to 1. Okay, so in order to show that this operation, this set is closed under this operation, it is enough, and it is enough to prove this. It's enough to show that if this is the case, A is equal to 1 or B is equal to 1. So let us do that. A star B is equal to 1, but what is A star B? You see it here, so this becomes A plus B minus AB equals to 1. I move 1 to the left, it becomes a plus b minus ab. Very simple algebra. Okay, between these two, I factor a minus a out. From here, positive b is left. From here, minus 1 is left. And b and minus 1, I combine them. Now you can see b minus 1 is in common, so I factor it out. From here, 1 is left. From here, minus a is left. Now the product of two numbers, two real numbers, is equal to 0. This means that either this one is 0 or that one is 0. So this means either a is equal to 1 or b is equal to 1. So I was able to assume this and conclude this. And this is the contrapositive of that one, which is equivalent to this one. So yes, this star is still a well-defined binary operation on the new set R without number 1. Okay, so I have a binary operation. The next axiom is associativity. So how should I check that? Okay, so I would say that if A, B, and C are all coming from this new set, I want to convince myself that A star B first and then star C becomes equal to A separately with the result of B star C. I need to convince myself about that. Okay, so I start from the left-hand side to see how it goes. The left-hand side, because of this pair of brackets, this star operation is prioritized. So I will do this one first. But what is A star B? A star B is just defined there, so I would write it. It becomes A plus B minus AB and then star C. But how can I do this one now? So you have to interpret this in a correct way. The first number plus the second number minus the product of these two numbers. But here, this is my first number. So this becomes the first number plus the second number minus the product of the first and the second numbers in this order. Okay? So let me open it up. Let me write it a little bit more organized. A, B, and C. I write them next to one another. And then what do I have? I have a minus AB here. But now I multiply C and a minus sign, so it becomes minus AC. The next one becomes minus BC, but the last one becomes plus ABC. So let me call it number 1. And now I determine the right-hand side. So in the right-hand side, the pair of brackets is around the second pair. It prioritizes this operation first. So I copy and paste this one for the time being. But instead of B star C, I use the definition again. So the first number plus the second number minus the product of them. And now I use the definition of a star once more. This is my first number, this is my second number. So it becomes the first number plus the second number, and then minus the first number multiplied by the second number. Okay, and let me open it up again. I have A here, B and C coming next. And then I have minus AB. I want to make it sure that it's exactly like that. So I will reorder them a little bit. So minus AB. And then I have minus AC. I also have a minus BC. And then minus A times minus ABC is plus ABC. And if I call it number 2, just compare number 1 and number 2. You can see the left-hand side is equal to the right-hand side. So number 1 and number 2, comparing them, gives me that, okay, the left-hand side is indeed equal to the right-hand side. So associativity is proved. And of course, you see that this operation was also associative on the set of R, because nowhere I have used the assumption that A, B, and C are not 1. So this binary operation is associative on this set as well as on the original set of the real numbers. Okay. Now, the next step is to check the identity element. Again, I claim that my identity element is still 0. Okay. By the way, if it is hard, you cannot guess. So, for example, you go to a scratch paper. So let me do it here. in this case, it is very easy to guess what is the identity element. But if you don't know how to guess, if the binary operation is hard enough, I would say that this means that for every number, every real number chosen from my set, so it means that A is not equal to 1, okay? So A is an arbitrary element in the real numbers except 1. A star E should be equal to A, E star A should be equal to A itself. Let us pick one of them. So A star E equals to A. A star E becomes A plus E minus AE is equal to A. And this A and that A are cancelled. And then I am looking for E, so I have to solve an equation. I factor E out. 1 minus A equals to 0. So be careful here. Either E is equal to 0 or A is equal to 1. Okay? But because A is not equal to 1, this cannot work. Then it means that E should be 0. And by the way, when I promised you that you will understand how to detect that 1 is the element to be blamed, is from here. So here I knew the answer, so I started the problem because I have done all these things in my scratch paper. But now, if you wanted to do this problem yourself, you had to do something like this when you want to check the axioms of being a group, and then you realize that this 1 is problematic. Because if A has the possibility to be 1, then there is no guarantee that I have an identity element, necessarily. Okay? Okay, so now you understand that. This is not hard to understand, but now we know that E is 0, so I would simply claim that for every A in my set, okay, 0, A star 0 equals to 0 star A is equal to A itself. But that is very simple now, okay? I start from here. A star 0 is equal to A, the first number, plus the second number, minus the product of the first number and the second number. But that is just simply A. And you can immediately realize the second one is also true. So we were able to show that no matter what A I choose from this set, 0 is the identity element. Okay? The next one is the inverse. Okay, guessing the inverse, probably we have to work it out. So I go to a scratch paper, I choose a number from my set. It means that A is a real number which is not equal to 1. And then I ask myself, is there any number in my set so that A star A prime equals to A prime star A equals to the identity element which we discovered to be 0. Okay, so let us see. Let us start with one of them. This is a scratch paper work, okay? So you write A plus A prime minus A prime equals to 0. But you are looking for A prime. So A is a given real number, you can imagine that, which is not equal to 1, and then you are looking for its inverse if possible. So I move A to the other side, and between these two, I factor A prime out. And I move this to the other side. Okay, I am looking for A prime, so I have to isolate my A prime. Then I have to divide by this coefficient. Am I allowed to divide? To divide, I have to be certain that this is not equal to 0. How should I know that? Because A is now chosen from my set. This is another indication that 1 is the culprit, okay? So, because A is not equal to 1, I can simply divide by 1 minus A. And then if you don't mind, let me multiply by an extra minus sign. So this will be it. Now we can simply claim. So this is the scratch paper. And then you can write here, let A be in my set. It means that let A be a real number which is not equal to 1. We show that expression, A over A minus 1 is the inverse of A. Yes? Okay, and then you know what to do we have to check that A star, A over A minus 1 is equal to A over A minus 1 star A, and this is equal to the identity element 0. Okay, so I didn't guess this one. Guessing the identity was not hard, it was simple, but might be guessing the inverse was a little bit harder. So I went to scratch paper, I did it, found it, and then I proved my claim here. So how should I do that? For example, let us check this one. A star A over A minus 1. According to the definition of the binary operation, I have to write the first one plus the second one minus the product of the first one and the second. And we have to simplify this. Okay, so how can I simplify that? The common denominator is A minus 1, and then A minus 1 will be multiplied here. A minus 1 compared to this, nothing has changed, so I copy and paste this A part. Nothing has changed, minus A times A is minus A squared. Then I simplify the numerator, so it becomes A squared minus A plus A minus A squared over A minus 1. And this A and that A are gone. A squared minus squared 0 over A minus 1, which is 0. And of course, you can simply prove this one as well. Okay, so we did some scratch paper work, found it, and proved the claim. So far, we have proven that R minus 1 and the binary operation is indeed a group. But now we also want to prove that this is abelian. Okay, so in order to prove that this is abelian, it means that I have to choose A and B from my set. So assume that A and B are real numbers not equal to 1. I have to convince myself that A star B is equal to B star A. But of course, this binary operation is still commutative if I consider R. Yes, you will see it's very simple, yes? Because if I ask you what is A star B, you will tell me it is A plus B minus AB. And when I ask you what is B star A, you will tell me it's B plus A minus BA. But these are real numbers, so there are no difference between them. So it means that, and then you see that I haven't used this assumption. So it means that this binary operation is also commutative on the original set R as well. Okay, of course, you can, if you know that this is going to be an abelian group, for example, you can prove the commutativity first so that you don't have to actually consider these cases. And of course, we know that in most of the books, they talk about the left and right identity element, the left and right inverse element, but you can prove that the other two can be derived from the other axioms. For example, if I can prove that I have a left identity, yes, and if I can prove that I have a left inverse in every group, and of course associativity should be checked first, closeness should be checked first, then it means that I will have a group. So that AE is equal to AA, and that AA prime is equal to BE can be derived from the combination of all these axioms. Okay, in any way, we were able to show that 1 is the problematic one, but we also showed that when we take it off, then I will have an abelian group. So this means that 1 is the only element to be blamed for. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.